The R codes posted provide a detailed, practical workflow for automatically preparing and analyzing large-scale survey data like PISA. First, in the file auto-discovery and meta-diagnostics stage, the goal is to automatically distinguish which files in the PISA folder of multiple set files belong to the cognitive side, including PVs, and which belong to the weights/questionnaire, QQQ, side, without human intervention. To do this, instead of reading all data in each file, it quickly scans by reading only the column names, checking for the presence of PV patterns with regular naming such as PV1 Math and PV2 Read, the inclusion of domain keywords like reading, mathematics, and science, the inclusion of score-like keywords such as score, scale, theta, abiel, professor, and level, and the presence of CNT, GNCHID, constituent, join keys, FSTU, main weight, and W_FSTRXX/W_FSTRX, replicate weights. As a result, files with many PV or domain columns are ranked as cog candidates, and files with clear weights and replicate weights are ranked as QQQ candidates. Next, the purpose of the load-only minimal columns and then merge stage is to save memory and speed by not reading all columns in the massive PISA files. From both files, it reads only the common keys and necessary variables, weights, replicate weights, PVs, then joins on the keys. At this point, it standardizes the types of CNT, GNCHID, and GNTs to each character before the join, and it takes care to verify via messages whether the number of rows changes after the join if there are duplicate or missing keys. Then, the goal of the replicate weight cleaning and validity filtering stage is to refine the replicate weight matrix to a state that is numeric, finite, with columns of all zeros removed before it goes into the design object. Specifically, it forcibly casts to numeric, replaces non-finite values, na/nth, with 0, removes columns where all rows are 0, as they are not substantive replicate weights, and also removes rows where all columns are 0, since replicate estimation is impossible. As a result, it secures the remaining list of replicate weights, reps_kept, and the filters do align to them. In the stage of creating a JK1 design object with SVRP design, the key point is that PISA typically distributes JK1, jackknife, replicate weights, so using them is necessary to reproduce official variants and SE. The settings use type equals JK1 ems equals true, specify scale equals J1/J and rescales equals 1 based on the number of replicates J to prevent warnings, and set combine.weights equals true, assuming that the replicate weights already follow a combine weighting scheme. With this day object, calculating SVMean, SVCOM, and similar estimates yields correct standard errors and confidence intervals that reflect the complex survey design. The purpose of the PV candidate auto detection stage is to automatically collect PV1, PV10 for read, math, and C by name patterns, even if PV variable names differ slightly across files. It does this by finding with regular expressions PV, read, PV, math, and PV, SCI, extracting the numbers, and sorting them in order from 1 to 10. In the quick diagnostic graph with a single PV stage, it is efficient to first plot only the country-level mean using PV1 to quickly verify that the pipeline functions correctly. It computes weighted means by CNT using SVB, and because the names of the mean and SE columns in SVB results may vary by environment, it safely selects column names using a dynamic identification logic, then visualizes bar charts with 95% confidence interval error bars using ggplot. In the stage of strengthening standard error, SE, extraction, two paths are presented. Either receive the variance column, var, with keep.var equals true and compute SC as sqrt_var, or use the survey, SE, function to directly extract SC from the SVB results. The latter is recommended due to lower environment dependence. In particular, if columns come in as character or factor, they must be converted to numeric before calculation. The official PV combination stage follows a procedure that combines within and between. PISA's plausible values, similar to multiple imputation, compute the mean as the average of the PV means, and total variance as the sum of within, the average of variances, and 1 plus 1/k middle dot between, the variance among PV means. The implementation flow is to compute group level means and variances for each PV, bind them in long form, and summarize by group as PV_mean equals mean underscore PV, var_within equals mean var_PV, and var_between equals var mean_PV. Then derive the final SC as PV_say equals SQRT var_within plus 1+1/k, var_between. The advantage of this method is that it simultaneously accounts for replicate-based variance, sampling uncertainty, and variation across PVs, measurement uncertainty. In the country comparison visualization stage, it generates bar charts with 95% confidence intervals using PV_mean and PV_say from the PV_mean_OECD_V2 results, and for consistent interpretation, the single PV graph is used for rough checks, while the combined PV graph is used for official comparisons. Finally, in the practical tips and error prevention stage, it recommends checking the mean, SE, and var column names each time with names df and strdf, outputting candidate common columns for manual specification if join keys differ, ensuring that columns of replicate weights that are all zeros are removed to prevent variance calculation errors, and, when memory is limited, reading only required columns or testing with the country subset before running the full process. In summary, this pipeline follows the flow of automatic file identification, selective loading, replicate weight cleaning, JK1 design, construction, single PV check, official PV combination visualization, and is designed to safely and reproducibly handle large, complex survey data like PISA,